I don't know, the phase of the moon or what your astrological sign is or something. But some computers, you hit the function F9 key. Some computers, you just hit F9 and yeah. Oh yeah, pass those out. Anyway, you can also, if for some reason it isn't working, if you just go up here and hit the save button, well, at least sometimes that will generate a new set of random numbers. So all you're doing in this exercise, and let me have one of those handouts just to read for a minute, is just working through generating 10 sets of distances. So here I put in beam C is 0.5, so 1 over beam C is 2. You expect the distance to be 2, that's the theoretical average. Well, in this particular case, the mean was 2.1 and the sample deviation was 2.5. So, you look here and here's the actual values. If we generate another set of numbers, well, this time, the mean of all the numbers was only 1.39, standard deviation 1.6. When you play around with these Monte Carlo things, you do your little experiment, you say, well, I'm expecting 2 and I only got 1.39. That's pretty far off, so it must be something wrong. No, try it again. There we got 2.5, we were expecting 2 and the variance was 2. So there's a lot of variability there. So in the first exercise, you just run through this like 10 times or something, generate a bunch of averages and sort of, look at here's the sample means coming from this column for 10 different trials. And then I averaged, let's see, that was for C equals 2. So anyway, I just looked then, does the average of each of these sets of 10, does that start getting closer to 1 over C? And you're just getting some feeling for how big the variability can be. And that if you really wanted to get a value that was the theory of 2 plus or minus 10%, say, you really have to trace a lot of rays to get enough to get the statistical noise down. So that's the one spreadsheet. Then the other one, the error propagation one, what I've done there is I've programmed in, let's see, can we get that big enough to read here? Probably not. Yeah, here we go. Yeah, let's try 150%. Okay, maybe you can read that. Maybe let's crank it up a little bit more. Is that good? Okay, well, when you're 74, that's not good. When you're 30, it's good. Okay, anyway, from the single scattering approximation, which we really haven't talked about here, but it says that the remote sensory reflectance is basically BB over A plus BB. And in fact, I should pull up the actual notes here so you can see the real equation. Yeah, so the single scattering approximation says RRS is BB over A plus BB. Then there's a term that depends on the phase function, the backscatter fraction, and then there's a 1 over 1 plus cosine of the sun angle. That's what it's actually equal to first order. We've always just been saying proportional to BB over A plus BB, but there's this other stuff. So what I did was I programmed a spreadsheet where you're going to put in A, you're going to put in BB, you're going to put in this thing, and you're going to put in the sun angle with some distribution of errors about the mean values. So when you come down and look at the spreadsheet, for example, you can put in A as being 0.1, plus 20% error here, BB like 0.007 plus plus or minus 0.001, that phase function term 0.11 plus or minus 0.01, sun angle like 40 degrees plus or minus 0.5. And then it will take those values, plug them into the formula, and generate 1,000 values of RRS. So if we just look at doing that, so here in the green boxes, if you want to change the absorption coefficient, or you want to change the standard deviation and from say being 0.1 plus or minus 0.02, you could put in here, 0.2 plus or minus our standard deviation of say, I don't know, 0.01, something like that. And then you have to click the button and generate a new set of 1,000 numbers, which are all strung out down here for 1,000 rows. And then the idea is to create a histogram of what that distribution looks like. So here's RRS, 1,000 simulations. Here's the frequency at which various values occurred. So a couple hundred times this value, a couple hundred that time, not very often that. So for those particular values, I'm getting an RRS that's somewhere around 0.004, 0045, but with a pretty big spread here, 0025 to maybe up to 007. It would be really nice if Microsoft could figure out how, when I generate a new set of numbers, it will update the histogram. It doesn't do that. So the handout has a big explanation at the back, the appendix, of how Microsoft tells you to generate a histogram, and it's utterly ridiculous. So it's the best thing to do, since you guys are all quite sophisticated computer people, is where did this go here? ABB. Yeah, here's a column with 1,000 RRSs. Just cut and paste those, stick them into MATLAB, which has a histogram routine, or IDL or Python routine or whatever, and just give that bunch of RRSs, 1,000 of them, and say, make me a histogram. And you can do it in less time than it takes to read the directions on how to do it in Microsoft or in Excel. And then for a run, we put in an absorption coefficient up here of 0.2, standard deviation of 0.01. So here's all the absorptions that were created. Here's the backscatter values, the phase function values, the sun values. And so, the sun angle of 35, 39, 36, et cetera, et cetera. So, and then the corresponding RRS values. And then I just built in the bin sizes here, which are maybe good enough. So anyway, the idea here is to do some runs, generate some of these histograms, see how big the spread is. And then one of the problems is it says that if you really wanted to get RRS that's accurate to, what did I say, 10% accuracy that you're going to use to validate your satellite retrievals. Well, then what you want to do is back up. You'll do some runs here. You find out I'm not even close to having a value that's within 10%. So you're going to back up, change, let's say, the absorption coefficient, and then how small of a standard deviation do I need to have on absorption, backscatter, the phase function term, the sun angle, so that the resulting RRSs will have a histogram that's a 10% error. And when you find out how accurate, you have to measure those IOPs to get a 10% accuracy in RRS, you'll realize the whole process of satellite validation is hopeless. So you're going to have to really do good ACS scattering corrections. But anyway, so that's what to play with there. And then the third thing is there's this in the BMC 3D thing, there's code here, and in the run directory, there's this executable, which, as I said, works only on Windows machines. And then what we'll do with that is, if you don't know how to start up a command window, what will happen is if you just click on this little interface will come up, you'll enter your data, it'll run, and the window will close, and you won't be able to see the answer. So what you want to do is do something like type CMD here, command thing. It'll come up with a command prompt. You can pick that guy and open it. And then what you want to do is change the directory to wherever you have this BMC 3D code with the run directory. So on my computer, and I'm just going to close this window and use one I already have up here. Let's see. Okay, so I would do like CD to, what did I call all of this? CD2, whoops, main 2021 class. Monte Carlo Lab. Screw up. Yeah.
If you click on the path file right there on the, looks like the search bar, you can just copy and paste it over.
Yeah, probably. You know, I have all this stuff. If I
Yeah, triple click on the run button.
Oops. Okay. You know, a trick. I set this up once and then I never looked at it again. So what's the trick there?
So if you click there and then Control C,
No, excellent.
CD space, Control V.
Hey, man, learn something every day. Okay, now I'm in that run directory where the thing is. So now if we just type in the BMC 3D/SV, it will start running. And this has a really simple little question and answer interface. It's not like Hydrolyte, you know, nobody but me supposedly uses this thing. So I've never gotten fancier. But what you can do is just accept that we're going to put in the parameter values from this defaults wall file, and the geometry we're using here. Whoops. Let's go to, hang on here, the lab. So there's the little coral reef geometry. There's a flat surface and a vertical wall. You're going to put in like, how deep is this surface? What's its reflectance? What's the reflectance of the wall? Wind speed on the surface and so on. And then you can specify where the detector is, what kind of detector it is, what direction it's pointing, and so on. So the way it works is the theta direction is downward, just like in Hydrolyte. So if you put in a detector here in a minute with the theta of 0, it means the detector is pointed downward. So it's going to be measuring upwelling light. If you want to simulate ED, for example, the detector's looking upward, that's the 180 degree direction. and collecting light going downward. And so anyway, and then the front of the wall here is at X equals 0. So if you put the detector at, say, X equals 10 meters, then it's going to be 10 meters in front of the wall or 100 meters or whatever. And so you'll be doing runs where you do things like put the detector at 1 meter, 2 meters, 5 meters, 10, 100, whatever, looking upward or looking downward or looking towards the wall. And that's how that works. So there's the geometry. And then if we go back to here, you can just accept this first thing. Hang on here. Write that down here. Okay, oh yeah, so it says, is that okay? You can just hit enter and that's the same as yes. You can give a root name for the file. So if you don't like test1, you hit no and enter like run one, for example, and it'll use that to create file names like Hydrolyte does. You can give your file a run some name. If you don't like the default, just say first lab run example. Same as Hydrolyte. Okay, so then we get down and it says, here's the coral reef wall parameters. The tops, it's 10 meters deep. We're going to trace rays until a ray goes to greater than 50 meters and then just throw it away. And then the reflectance of the top in this case was 0. It's a black thing. The wall is black. Now, if I wanted to put, for example, let's say I don't like those values. So it'll say, what's the top of the coral reef? Well, let's put it at 5 meters. And how deep? I'm going to trace rays till they go to 50 meters deep, let's say. And then the reflectances for the top. So I'm going to say the top is 20% reflectance and the wall is 10% reflectance. Okay. Now the first runs, we're going to compare with Hydrolyte. So what you want to do is put the sensor like 100 meters or 200 meters or something in front of the reef wall. Then the reef is so far away, it doesn't affect your answer. You're really in a 1D geometry and you can compare with Hydrolyte. Then you convince yourself that this code puts out the same answer as Hydrolyte. Then you can back up and put the sensor closer to the reef wall and see what happens to the light field. And here we're putting it way out in front. The Y value doesn't matter because the geometry is the same in the Y direction. And we're putting the sensor at 10 meters depth. Okay, let's just take that. And then it says the default detector orientation, nadir angle theta D is 180. So it's measured from the nadir, 180 is the sensor is pointed upward. And in that case, phi doesn't matter. But you could put the sensor at 90 degrees and phi at 90 degrees, and you'd have a sensor that's looking parallel to the reef. If you put theta of 90 degrees and azimuthal angle of 180, your sensor's looking at the reef. So anyway, let's just take those. It says, what kind of detector do you have? Well, it's a radiance detector with a top hat response and a 5-degree field of view. So that would be fine for computing LU or LD or radiance in some other direction. Maybe we want to compute ED. So don't take those values. And there's options. You can have a Gaussian tube, cosine response for ED or EU, a uniform response over 2 pi or uniform for 4 pi. So if you wanted to compute E0, scalar irradiance, you'd pick that one to compute ED, just hit a 3 here. And it says, I want detector type 3, and that's what you'll get. Then you put in the absorbing and scattering coefficients. Okay, let's just take those. Petzold average phase function, sure, use that. Wind speed, yeah, fine. We pick the sky model. It says semi-empirical, or you can do an idealized sky if you want to do things like put a sun in a black sky or whatever. Otherwise, this is the same as the RadTrans sky model, except there's some little numerical differences that'll make 1% or so. But let's just accept that. Cloud cover 0%. Let's make a clear sky, same as Hydrolyte. A default wavelength, yeah, let's do the runs at 400. What the heck? And then the other thing is, how many rays do you want to trace? In this case, it's 500,000. You have to put in a seed for the random number generator, and you can just leave this as 10 to the minus 6. This says once the weight, which starts out at 1, gets to less than 10 to the minus 6, throw the ray away and start a new one. Well, let's say maybe I don't want to do that, so I'm going to say no. Maybe I want to do 500,000. Maybe I want to do 50,000 rays. Then I have to generate a seed for the random number generator. I don't know. Let your cat walk across the keyboard or something. So there's my seed and 1.e to the minus 6. So, and then it says, do you want to overwrite the old defaults file? You know, a lot of times you're going to just make the same run over and over again, but change the number of rays or change the seed. So you can say, sure, save it. And then it says it's running. And then there at the end now, we finally get some answers. So what you see here is it says, okay, there's some little checks there and those numbers are right. Then there's a big table that says state of the sun, phi of the sun, the estimate of whatever you were computing. In this case, it was ED. How many rays did the sun quad get? And then what was ED in the air? Now, here's the deal. You're doing this backward Monte Carlo thing. You're sending rays out of the sensor. They're going up and eventually getting to the sky. And just experience shows that if you want to get a good estimate with fairly small amount of Monte Carlo noise, you need to get at least 1,000 rays connecting your sensor and the quad that the sun is in. And that gets the Monte Carlo noise down a little bit. If you were going to publish a paper, do it again and have 10,000 rays connected. But what you're seeing here with only whatever I trace 5,000, there's only a few dozen rays. So these numbers would be really unreliable. So let's go back and let's just do another run. It won't take long. Okay. So we'll just run this guy again, and we can just click through the whole thing and get down to here and say, no, I want to do 500,000 runs or rays with whatever and 1.e minus 6 and let that run. And this might take, a minute or something now. Oh, yeah, sorry. And I've actually done runs here where I put the run in and I go on vacation for a couple of weeks and I come back and it's still running. So it can get pretty ugly to get really good accuracy. Anyway, there will be some runs here where I just suggest, do some runs here with the sensor in different directions and compute ED and compute LU and, look at the Monte Carlo noise and these things. And how many rays you could trace in there. That kind of thing. So, okay, so let's look at the answers again here now. So this is a table that has the answers for each possible sun angle. So here, theta sun, phi sun is 0. That's the zenith, would be ED that you could compare with the Hydrolyte with the sun straight overhead. And notice there's 2,500 rays came out of the ED sensor and actually made it up to where the sun was. So you can probably pretty well trust that number there. And these numbers here, so here, if you did a hydrolyte run with, say, the sun at 30 degrees, then there's 30 degrees there. It's saying the ED is 2.6 watts per square meter per nanometer for that sun angle and whatever the depth and the IOPs and such were that we had. And we're getting, 1,500, 2,000 rays here. That's probably a pretty good number, but play around with it. Do the same run with maybe do it 3 or 4 times with different seeds, just see how much variability there is. And then duplicate the run here with a hydrolyte run, use the very first IOP model where you just put in total absorption, total scattering, pick a phase function, pick a sun angle, etc. Do a hydrolyte run, and then you could pick this number here, say the 30 value, and then go look at the hydrolyte output and get the ED at that depth and see how they compare. So that's it. I think enough said there. I'll let you play with this stuff. And there are some little statistics down here that I started 500,000 rays. It ended up tracing 116 million rays as they bounced around. And then there were 338,000 actually made it through the surface and got tallied. There were 260,000 that underwent total internal reflections. None of them actually made it over to the reef wall because our sensor was out there at 200 meters away. 106,000 of these guys bounced around and headed down and finally just got killed off. And there are weird things. Sometimes anomalous rays can occur, but there weren't any. And it took 38 seconds to run. Okay, that's it. So go to it, play around with it, and then your little report tomorrow will just show some histograms and whatever wisdom you've developed about how many rays you have to trace to get a good ED versus a good LU, and what happens as you move an ED sensor up close to the wall of the reef. Maybe let the reef top be at 5 or 10 meters, put the sensor down at 20 or so. And when you put the phi direction at 0, the sun is in front of the reef, so the reef will be in the sun. And if phi is 180, the sun is behind the reef, so the wall of the reef is in its own shadow. So when you come from here, you'll go into that shadow, and then you'll see what goes on. And so that's what it's all about, and we'll see what you come up with tomorrow. By chance, it's Macintosh, which format compiler, sometime this week we might try to compile it to stove and see if it runs on that. It should. So I have very bad experiences with Windows computers, even worse without computers. Windows people who couldn't get Hydrolyte installed and give us a special. Anyway.